Hi. Hello, everyone. I'm Adam, and I'm here to present work I've done jointly with Justin Frank and William Bowman of University of British Columbia. So to start off with, we all know that WebAssembly is a new language that is meant to be used for performance-critical browser applications. So on one hand, we want it to be fast, but we also want it to be secure because this is code that you might be downloading from anywhere on the internet. So you don't want it to be able to crash your browser or steal your secret data. And WebAssembly has nice security properties that will ensure this doesn't happen. But unfortunately, these properties rely on runtime checks. And these runtime checks might be unnecessary, and when they are unnecessary, they will slow down programs. These dynamic checks have been identified as a significant cause of the performance gap between WebAssembly and native code. So what can we do about this? Well, in the past, one idea was to attach a checkable proof of correctness to code. This is proof carrying code. And this basically solves our problem because this easily checkable proof of correctness can ensure that these dynamic checks are necessary. But on the one hand, generating these proofs can involve a lot of developer effort. And on the other hand, these proofs can be quite large, even larger than the size of the code itself, which isn't quite great when we want to be downloading this code from the internet. And so, a much larger file size is not optimal. Another direction we can look in is using something like TIL. TIL use typed intermediate languages in the compilation of SML code, and we're able to achieve significant optimizations relative to the SML New Jersey compiler. But this doesn't get us down to the assembly level for a language like WebAssembly. What does is something like F2Tal, which took a language, System F, which is a typed functional language like SML or F#, and proved type preservation down to a typed assembly language. And this doesn't quite get us what we want, though, because they ensured safety properties, but they weren't able to do optimizations. They weren't able to use these types to eliminate dynamic checks, and we want to eliminate the dynamic checks. And the reason for this, why they weren't able to eliminate the dynamic checks, well, let's look at what a type system is. And the way I like to think of a type system is a way of answering questions about the behavior of a program. So you can ask a question like, is this an integer? And that's true of programs like 1 or 5 plus 6, or this function call, where here the lambda is just a function that takes an argument x and returns x plus 1. And we apply that to 5, and that will end up with 6, which is an integer. And you can ask another question like, is this a Boolean? And you have that for things like true and x and y. But there are some programs where we can't answer any questions. True plus 5, that has no meaning. And applying 5 as a function to true. Both of these have no meaning, so they wouldn't be well typed. In this second case, applying 5 as a function is especially bad, because if you allowed this, then you might allow arbitrary code to be executed, because you have no idea what you're trying to execute as a function. But what about something like 1 divided by 0? Most type systems would say that 1 divided by 0 is an integer, including the WebAssembly type system. And the reason for this is that the type system is not expressive enough to differentiate between 0 and other values. So it's just looking syntactically and saying 0 is an integer, 1 is an integer, so their division should be an integer. A more expressive type system is able to answer more fine-grained questions. So not just, is this an integer, but also, is this greater than 0? Is something even, or is it equal to 5? And this allows us to ensure that something like 1 divided by 0, which is not an integer mathematically, it's not well-defined, would not be well-typed. And an expressive type system like this has been used previously in assembly languages, and this is detail. So what we want to do is we want to take this and add it to WebAssembly so that we can enjoy the nice safety properties without having these unnecessary dynamic checks. So we want to reduce the number of unnecessary dynamic safety checks. We want to ensure that the developers don't have to prove anything or take extra steps. And we want to ensure the same level of safety and security properties as we had previously. So let's take a look at the formal model of WebAssembly and see where these dynamic checks pop up. WebAssembly is a stack-based language, which means that the arguments to the instructions are implicitly passed on the stack, as well as the arguments to functions. There are some instructions, as we'll see, that take static arguments or type annotations, but when the arguments are not specified, then they come from the stack. It has nice structured control flow using function calls and blocks and branching. It doesn't have go-tos. And it is type and memory safe. And these are the safety properties that are partially enforced by dynamic checks. If we take a look at the different types of WebAssembly instructions, then we have numerical operators like addition, subtraction, and division. And then, as we saw before, we have to have a check for division by 0 because the WebAssembly type system is not expressive enough to capture that and say that dividing by 0 is not well typed. For control flow, we have, as I mentioned, we have blocks and branching and function calls and returns. We also have indirect function calls, and I'll explain a little bit what those are in a bit. But indirect calls require a runtime type check, and we'll see why that is in a bit. And finally, there are some memory operations, and you can do load and store into memory, and these, of course, require memory bounds checks. So these are the 3 types of dynamic checks that pop up. Now we'll jump into the syntax of WebAssembly. So WebAssembly consists of values or primitive values of the type T, which can be 32 and 64-bit integers and floating point values. We also have these function types, although they're not really function types, they represent a precondition and postcondition, as we will see. And this T star is the clean E star, like you might see in regular expressions, which just means it's a sequence of values T, which might possibly be empty. We use epsilon to denote the empty sequence. We have modules and we have functions, and here you see the function has this annotation, which is a function type, but again, it's really a pre and post condition. We also have a table, which is used for indirect function calls, as we'll see in a minute. Memory, there's also global variables, which I've omitted. There are many different types of operators, for example, binary operators, there are some listed here. And there are many types of instructions as well, some of which are listed here. And one thing to take a note of is this call indirect, which has a function type annotation as part of its syntax. And why is that the case? Well, let's take a look at how call indirect works. So on the left here, we see a table, and it has 5 different functions in it. And what happens is we will supply an index on the stack to call indirect. And then we will index into the table based on the value from the stack and call the function at that index. So if you supply 1, you call this function. And if you supply 2, you call this function. And the 2 functions you might call have different types. So because you don't necessarily know what the value on the stack will be, you don't know what type of function you will be calling. And because functions take their arguments from the stack, you don't know then what arguments should be on the stack when you do call the function. So the way WebAssembly handles this is that there's this statically provided type annotation, which is the expected function type. And then there's a runtime type check to ensure that whatever function ends up being called has the same type as the expected type. And this is used to check that the arguments that will be on the stack will have the correct type for whatever function ends up being called. So we can see that this first function here is okay, it has the expected type, second function as well. But the third function has a different type, so this would result in a trap, a runtime error. The fourth function is okay again, and then the last function is not okay. So now we can look at the dynamic semantics of WebAssembly, which uses reduction semantics. And what the WebAssembly reduction semantics range from configurations, which is this S, V star, E star, and then it takes a reduction step to S prime star, V prime star, sorry, S prime, V prime star, and E prime star. S is the runtime story, which holds information about functions, globals, tables, and memory related to different modules. V prime is the list of local variables, which we denote as values. So we say that the constant instruction, t.const c, is the representation of a value, v. E star is the list of instructions. It's basically the code we are executing, but it will also implicitly contain the stack, and it might be decomposed to reduce block bodies, as well as the bodies of function calls. And this little I annotation on this step or transition arrow is the module index I, which just tells us which functions, which globals, which table, etc., inside of the runtime story we're reducing with. And so as an example, this program is a contrived program. So you're unlikely to see this in real code, but it's an example of a case where we have this unnecessary division by zero check, where we should be able to eliminate it because we have enough information looking at this to see that it's unnecessary. So what this first instruction will do is it will push the value of the second local variable onto the stack. The second instruction will push the value of the first local variable. We index into the list of local variables using the statically provided offset. So get local run 1 will get the local variable at index 1, which is the second local variable. The instruction on line 3 is just a constant instruction. So although conceptually it pushes this constant value onto the stack, because it's already a value and the stack is represented as a sequence of values, as we will see, it actually won't do anything. Again, we have an instruction that gets the value of the first local variable. Then we get to this select instruction, which is a little bit more interesting. It's a ternary operator. So if the value from the fourth line is 0, then it will select the value from the third line, and otherwise it will select the value from the second line. And because the values from the fourth and second line will be the same, then if that's 0, it will select 1, and otherwise it will select a value that is known to be non-zero. So by the time we get to this division operator at the bottom, we should know that the second argument is non-zero. And for example, if we set it up in this way, where the first local variable at index 0 is set to 0 when we start executing this. Well, first we get the first the second local variable, which is 42, and push that onto the stack. We reduce the next instruction in the stream, which gets the first local variable, which is 0. And now we skip over this value, which is the constant instruction, i32.const1. And again, that's because, as we can see now, the stack is kind of taking shape at the top of our program as this list of values represented by these t.const, or in this case, i32.const instructions. So we do get local 0 again, and get the first local variable. And now we come to select. In select, in this case, because the conditional argument, the third argument is 0, it will select the second argument, which is 1. Now we do the division, and the division succeeds. There's no error. We're happy. And why is the WebAssembly language unable to detect this? So let's look at the WebAssembly type system. As I mentioned before, the types of instructions, which are these function types, as well as the types of functions, represent the shape of the stack before and after execution. So it really is just a precondition and postcondition on the shape of the stack. It tells you what values will be on the stack before and after you execute an instruction. See what this looks like for a simpler example where we have two constant instructions of a division. We know that this first constant will be a 32-bit integer. The second constant will produce a 32-bit integer. So by the time we get to division, we have two 32-bit integers on the stack. When division will take these two 32-bit integers, divide them, and produce a 32-bit integer onto the stack. And we can look at the WebAssembly typing judgment so that we can see how the typing rules work. And what this says is that under the module type context C, which stores information relating to the types of functions, the types of globals, the size of the table and the size of memory, then this, under that type context, then the instruction sequence, E star, has the type T star to T star, and this type is a pre and post condition. So you're saying, under this type context, E star expects these values T star to be on the stack before execution. And if that's the case, then it will produce in the post condition some other stack T star. Now we can look at the rules. So the rule for this constant instruction expects there to be nothing on the stack in the precondition, and then produces onto the stack a value of type T. And for the binary operation, we expect there to be two values of type T on the stack, and we produce a value of type T. And you might be noticing, hey, wait a second, in this type rule for constant, we expect there to be nothing on the stack in the precondition. Yet looking at the example I just showed you, for this second constant instruction, there's already this 32-bit integer on the stack. So there's these mismatched preconditions. And as I said, in the post condition, we expect there to be two 32-bit integers. So the way we get around this is using stack polymorphism. What stack polymorphism allows us to do is to compose together instructions by carrying around extra information about the shape of the stack beyond what a given instruction will modify. And in the previous example, this allows us to carry around the extra 32-bit integer from the previous instruction. And this makes sense because that instruction won't modify that part of the stack. So when you get to future instructions, that part of the stack will still be present. And these are the types of questions that the WebAssembly type system can answer. what is on the stack before and after execution in terms of primitive types of the values. Is it a 30, do I have two 32-bit integers before execution and one 32-bit integer after execution for the 32-bit integer division operation? And this is insufficient to give us to be able to eliminate dynamic checks. So we need something more. And that's where our work, Wasm-prechk, comes in. We model Wasm-prechk as a language, but we like to think of it as a specification for when it is possible to eliminate dynamic checks inside of a compiler. So in terms of the syntax of Wasm-prechk, we make a few changes. On the one hand, we use a different representation of types, as I will expand on in a bit. But this other change is that we introduce pre-check tagged instructions. And these are basically the same as the different WebAssembly instructions that require dynamic checks, except that these explicitly do not require dynamic checks. So we introduce this division pre-check instruction, which will know that the second value is not 0. So it knows that it will succeed in the division and not have to cause an error. We have a store pre-check and load pre-check, which knows that the operation is taking place within the boundaries of memory, and therefore it won't cause an error. And finally, we have call indirect pre-check. And this knows that whatever function ends up being called will have the correct type. So it doesn't need to perform this dynamic type check, and it won't cause an error. And this weird TF5 that I'm using here instead of a TF, this is just a Wasm-prechk pre and post condition. As I mentioned briefly, we use a different representation of types. So the questions we need to be able to answer with the type system are a little bit more complex now, they're more fine-grained. Now we don't just want to say, does the stack contain two values of type T? But now we want to know that the value on top, the second argument, is not 0. So how do we do this? Well, in general, we need to know what does the stack look like before and after execution? We want the same level of guarantees as WebAssembly. Now we also want to reason about the local variables, so we have a little bit of extra reasoning power. And we also want to be able to answer questions such as, how do program values relate to each other? For instance, for division, we want to know if something is greater than 0. For the memory bounds checks, we want to know if, given value is within a range. And for the call indirect pre-check, we want to know what are the possible functions we might end up calling. So how do we do this? Well, we could use something like a dependent type system. And a dependent type system really collapses the distinction between terms and types. Terms are types and types are terms. And this allows you to express something like a pair of integers where the second is greater than the first. So this would be helpful for division, for example. But the dependent type systems are very heavyweight, and we want to avoid any extra proof burden, well, any proof burden at all for the developer. So we want something a little bit more restricted. We also want something a little bit more restricted, so hopefully we can make it a little bit easier to reason about in a compiler in a browser. So an index type system, which is what is used in detail, is a restricted form of dependency. And what it does is it uses an index language inside of the type system to track constraints. And it has a different meaning. The terms in the index language have different meaning than the terms in the base language. So the way we design the index language for Wasm-prechk is that we use index variables, or variables in the index language, to represent program values. And this is both on the stack and local values, local variables, as we'll see. And these index variables get associated with these program values on the stack and the values of local variables using index types. So now we can look at the more formal model of the Wasm-prechk index language. So we have index variables, as I mentioned, and we have indexed types. And index types include the primitive Wasm type t, because we want to have at least the same amount of information as WebAssembly. But additionally, they include this index variable a, which basically represents a value within the index language. So it represents a value from the base language, but then the index variable is used within the index language. We have index terms, which are how we express relationships between different index variables, which represent program values. And an index term can be an index variable, it can be a constant value, and we include the type of a constant value. Or it can be a binary operation on two index terms. And this is one of the more common ways of expressing a relationship between two values, two or more values in the index language. We have propositions, which are essentially constraints. So the most simple one is the equality constraint. It just says these two terms are equal. And then we have this if constraint, which is kind of a shorthand, which is useful for dealing with the select instruction, as we will see in a bit. And we have some common first order logic constructors that are used to combine information, combine constraints, such as and not. And then we have this constraint set, phi, or phi, rather. And this phi comma p is basically the syntax for adding a constraint to the constraint set. Lastly, we have the index environment gamma, which isn't really important for the high-level intuition of how the type system works. It's really just allowed for bookkeeping. So as an example of the type system in action, now that we've seen the index language, let's look at that same program from before, where we know that dynamic check is unnecessary. And let's see what the Wasm-prechk index language will do with it. So we begin by getting the value of the first local variable. But now the local variables, we know more than just their type. We also have this index variable associated with them. So we have A0, a local variable, which is associated with the type of the first local variable, associated with the value of the first local variable. And A1 is associated with the value of the second local variable. So now when we do get local 1, we're going to push a new value, B1, onto the stack. And we're going to associate B1 with A1. In fact, we know that they're equal. So we add an equality constraint that B1 is equal to A1 to the constraint set. And here I'm using the convention that an index variable on the stack will be B and then a number, where that number is the line number, which introduced that index variable. So B1 on the stack represents the value introduced by the first instruction, get local 1. So the second line, we get the value of the first local variable, which is A0. So now we create a new index variable on the stack, B2, and we associate that with A0. We say that B2 is equal to A0 in the constraint set. Now we're at this constant instruction, which pushes a constant value 1 onto the stack. So we introduce a fresh index variable, b3, and say that b3 is equal to the constant value 1, which we know is a 32-bit value, and we add that to the constraint set. We have get local 0 again. So again, we introduce a fresh global variable onto the stack, sorry, fresh index variable onto the stack, which is associated with the local variable, or rather the index variable A0 associated with the first local variable.
Adam, can I ask a question?
Yeah.
Is there a reason why you're using equality constraints rather than reusing indexes?
Yes. It's useful mostly for the proof of type safety, because if you reuse the same values, then when you do reduction, you end up with constants instead of local variables. So that proved to be difficult. There's not really much of a reason statically why that's the case, but it made reasoning much easier.
Okay. Thank you.
So this select operation, which is the ternary, and this is where we use the if statement from before. So it will produce a fresh index variable, b5, which will be, and in this if statement, we see that b5 will be equal to b3, the second argument to select from the stack, if b4, which is the conditional argument on the stack, is equal to 0, and otherwise b5 will be equal to b2. And what this means, as we saw before when we stepped through this example as part of reduction semantics, what this means is that b5 cannot be equal to 0. And the reason is that b2 and b4 are equal. So if b4 is not 0, then in this false branch, we know that b4 is not 0, and therefore, since b2 and b4 are equal, b2 can also not be equal. Sorry, b2 can also not be 0. So then we know that b5 won't be equal to 0. And if b5 is equal to b3, well, b3 is equal to 1, which is not 0. So then we do the division, and we're left with just one index variable on the stack, and it's of type I32, and it is just equal to b1 divided by b5, because those were the arguments on the stack. Now let's look at the typing judgment for Wasm-prechk, so that we can look at the type rules for these instructions.
Adam, can I make this observation?
Yeah.
It seems like basically the high-level idea is you're moving a lot of the type checking essentially into the constraint set. Is that a way to summarize it?
Yeah.
So you're saying, okay, here's the things we learned from these typing rules, push that to the constraint set, and then use essentially constraint satisfaction reasoning to figure out does this type check or not. Is that a reasonable summary?
Yeah, exactly. We're pushing all these constraints to the constraint set, and then when we come to the pre-checked instructions, we use constraint satisfaction.
Right. Thank you.
Okay. So when we look at this typing judgment, we have, as before, C, which is the module type context, except now it's an index module type context, because the types of functions are now indexed function types as opposed to regular WebAssembly function types. But otherwise, it's the same high-level structure and contains the same information, but represented differently. E star is still just the instruction sequence, but now we have a crazy amount of stuff going on in the precondition and postcondition. We have ti star instead of t star, and this is just the sequence of index variables that represent the stack. L is the list of local variables, which are also represented by index types. So the stack and the representation of local variables has the exact same structure. Although we use the shorthand L because in most typing rules, we don't touch the local variables. Gamma, as I mentioned before, is the index environment, and it stores index type declarations. So it's useful for reasoning about freshness of index variables because it tracks all of the index variables we've seen so far. But again, it's not really important to the high level intuition. It's mostly around for bookkeeping. And we have gamma, which is the set of constraints. And the reason we have phi and gamma both in the precondition and postcondition, well, as Ross said, we're adding constraints to the constraint set. So in the precondition, sorry, in the postcondition, we will have potentially more constraints than we did in the precondition as we learn things by type checking instructions. So now we can take a look at the typing rules.
Yes, one more question, Adam. Sure. In your postcondition, can you refer to any of the index types from the precondition?
Yes.
Okay, so you have some sort of dependent reasoning along that line.
Yeah.
Okay. Just want to check. Thanks.
Yeah. Right, so the rule for constant, if you squint a bit, it looks sort of like the WebAssembly rule for constant, in that we have an epsilon to represent the stack in the precondition, and then we have something of type T to represent the stack in the postcondition. We carry around L because the constant instruction doesn't modify local variables. For gamma, we add the type declaration TA to gamma, and that's just saying A is now a variable, an index variable that we're using, and it's related to the type T. And in this precondition, A not in gamma is just ensuring that A is a fresh index variable. And then now all the way over on the right side, we're saying we're adding the constraint that A is equal to the constant TC into the constraint set phi. So that's what that phi comma equals A TC is doing. Similarly for the binary operation, the shape of the stack in the precondition is two values of type T, but now we have the index variables A1 and A2 used to represent them. And in the postcondition, we have a fresh index variable, A3, with also of type T, which is then constrained to be equal to the binary operation applied to A1 and A2. And I'll explain what those funky bars are in a minute because they also appear in the select rule. And as I mentioned, the select rule is where we see this if, which also has the funky bars. And these funky bars just mean that this is part of the index language, or these brackets rather. So that this is part of the index language. And what that means is that it's not a Wasm instruction anymore, but it's kind of a lifted meta function, right? They, ostensibly have they have the same syntax, but yeah, now it's not modifying variables on the stack, it's being used as this meta function. The rule for select has two values of type T, which are represented by the index variables A1 and A2 on the stack in the precondition, just like in the binary operation. But now we also have this conditional A3, which has to be a 32-bit integer. And in the postcondition, we produce onto the stack this fresh index variable A, and we have this if statement. So we say that if A3 is equal to 0, then we know that A is equal to A2. And otherwise, we know that A is equal to A1. This is the rule for composing a sequence of instructions with a single instruction. And keep in mind, E1 star might be empty, might be the empty sequence. And so what we're saying is, if the post condition of E1 star is the same as the precondition of E2, then we can append E2 to E1 star and have a precondition from E1 star and the post condition from E2. And finally, the rule for the division pre-check, as Ross alluded to earlier, relies on constraint satisfaction. And the reason we have constraint satisfaction is because we want to be able to say that the second value is not 0. But we might, in our constraint set, have more information than that. So we want something like if x is greater than 0, then we also know that if x is greater than 10, then x is greater than 0. And x is greater than 10, we call that stronger, and x is greater than 0 is weaker. So we say that one constraint set implies another constraint set if it is stronger than that constraint set. And yeah, these are used in pre-check rules to ensure that the properties hold. They're also used when checking against type annotations. A type annotation might have less information than you have gathered while type checking the instructions. So you want to be able to, you don't want to be penalized for knowing more than what you are supposed to know. So now we can look at the division pre-check rule, and we see that it is essentially identical to the binary operation rule with this additional premise that phi implies that A2 is not equal to 0. And this implication statement is the static guarantee of the runtime assumption that division pre-check knows that the second argument will be non-zero. This is what statically ensures that the second argument will not be 0. Of course, how do we know that this static guarantee actually ensures that at one time the second value won't be 0? Well, we've proved it in a type safety proof. In this type safety proof, it ensures that Wasm-prechk is as safe as WebAssembly. And specifically, the progress lemma is what connects the static guarantees in the type system with the knowledge we are supposed to have for reducing the pre-checked instructions. We've also shown that Wasm-prechk programs can be safely translated into well-typed Wasm programs using erasure, which isn't very interesting because Wasm-prechk contains strictly more information in the types, in the representation of types. More importantly, Wasm-prechk is backwards compatible with WebAssembly. If you take a well-typed WebAssembly program, you can use this embedding function to produce a well-typed Wasm-prechk program. Unfortunately, this embedding function produces extremely naive type annotations, which basically assume nothing. So you have no additional information other than what you can learn just from a sequence of instructions. And yeah, we've proved both of these properties. We have written a reference implementation of the Wasm-prechk type system just to show that it's feasible. We used regex to model the language, and we used Z3 for constraint solving. So here's just an example of a Z3 constraint, and I don't expect anyone to read that. There's a lot going on, and if you're not familiar with SMT2, then this won't make much sense. But the important thing is that this just shows us that it is tractable to turn the constraints that we generate into constraints that can be solved by an off-the-shelf constraint solver like Z3. In terms of the big picture, we want a practical, easy-to-use system. We want this to be useful for improving performance, while at the same time not requiring any additional kind of proof effort by a developer. We don't want people to have to do any work to enjoy the benefits of a more expressive type system. So really designing the type system was the first step. There's more work to do before we can get this practical, easy-to-use system. One nice thing is that the design is, as I mentioned before, we model it as a language, but really it's this general specification for when dynamic checks are unnecessary. So you can also think of this as a proven, safe static analysis tool. And one of the reasons for this is that we allow the type system to be parameterized by the kind of implementation of implication. So what we're saying is that you can use your own constraint solver, and it doesn't have to always be right. It can be an under approximation. So we do require that, if your constraint solver says that X implies Y, then it really is true that X implies Y. But it might be the case that X implies Y and your constraint solver says, no, X doesn't imply Y. And the reason for this is because you might have a much faster constraint solver and more lightweight to fit in the browser or a compiler that, is faster, but might not be as accurate. And as long as it's in under approximation, that's okay. You still enjoy all of the safety properties of the language. So in terms of the next steps, we mentioned proof effort quite a bit. And the problem is the embedding function, which is the main way we can get around the developer having to do any work, because we take existing Wasm code and produce Wasm-prechk code, but the Wasm-prechk code we produce has, very little information in the type annotations. So it would be nice to have a static analysis tool to generate better type annotations in the embedding function. Alternatively, Wasm-prechk could be a compiler target instead of WebAssembly, where the compiler from a higher level language like Rust, for example, would help to generate these type annotations. Additionally, I mentioned that we omitted global variables, and that's because it turns out they're very difficult to reason about. There's a lot of different ways that WebAssembly can cross module boundaries, and these different, basically every time a module boundary is crossed, you kind of lose the information you have about the global variables inside of your module. This is a difficult problem to get around. So what we do is we have the same guarantees as WebAssembly, in that we check that if you are trying to set a global variable, then the global variable is mutable, and that it has the correct primitive type T. But we don't have any new optimization opportunities on global variables. There's also dynamic memory resizing. In WebAssembly, you can try to grow the contiguous chunk of memory that you have, but we aren't able to reason about this because right now we just rely on the size of memory being static, the initially provided size, and to track the dynamic resizing of memory would require a stronger level of dependency than we have. So to recall from the beginning, we wanted a WebAssembly type system that will reduce the number of dynamic checks require no extra developer effort, and maintain existing safety and security properties. And that is what we have built with Wasm-prechk. Thank you.
Thanks, Adam. If I recall correctly from our meeting when we talked about putting the song together, you guys were interested in getting sort of feedback from people as to what would the WebAssembly team find particularly interesting in the system, like what kind of direction should you go. So this is a great opportunity for WebAssembly crew to sort of give feedback and sort of guide research in the direction that they would particularly like to see go happen.
Yep. I'm also happy to answer any questions about the material.
I have a question. I think you can hear me. So this is really cool. I want to confirm something. There's sort of multiple independent parts here that don't need to all happen at once, right? So I can say, you know, never mind the heap bounce check. Something involving guard pages makes that okay. Maybe so you can just work on the bits that eliminate the dynamic check on indirect calls.
Yeah, that's one possibility. I forgot to mention that the dynamic checks for memory bounds are the virtual memory tricks that make that, for 32-bit memory at least, not that big a deal. But yeah, for call indirect, that seems to be the more interesting and more problematic. The case where the dynamic checks are more problematic. So in the current system, there's no way to decouple those. But yeah, theoretically, well, I suppose there is a way to decouple those. In that, yeah, you could basically, you just never write pre-check on your memory instructions. You only add the pre-check tag to your indirect calls. And then you know, if you have memory tricks that would eliminate the bounce checks for memory instructions, then you wouldn't do the constraint solving. You wouldn't pay the constraint solving cost for memory instructions, but you would still get the benefit for indirect calls.
Another way you can control is right now you're sort of tracking like the full, like a constraint language for all of these, and you could have a smaller constraint language that's designed more specifically towards one or two, you know, some subset of these kinds of checks. Is that right?
Right. I think the indirect call, though, would probably, you would probably want the most constraint information for that one, because you know, for memory bounds, well, division by 0 is the simplest. You just want it to not be equal to 0, particularly. For memory bounds, you want it in a certain range. For indirect calls, you want it to be, you know, equal to one of a certain set, you know, one value from a set of values that are okay. Rather, you want to make sure that the index points to a valid function. So you don't necessarily have a range like you do with memory bounds. There might be gaps in that range.
So if you did that, you have a form of constraint solving, which is, I can't remember the term for it, but you haven't actually materially affected the tractability of the constraint solver by doing that. In fact, that's the biggest, for me, this is the biggest issue, is constraint solving is just as undecidable as anything else.
What's the decidability of your current constraint system? Do you know?
I'm pretty sure, although I'm not certain, that it's, I think, NP. I think it is decidable. I think because we stick to quantifier 3, so I think it's decidable.
But still, NP, and even in decidability, NP is is problematic for, well, it's problematic for to be able to go into spec, because that would make type checking be NP. Maybe less problematic for sort of more speculative or analysis kind of thing, because then you can sort of do your best shot and then take one, just stop running it after so many milliseconds.
Right. And keep in mind, oh, sorry.
Yeah, so, you know, we already have these tiers in the Wasm engines, right? So we have, so for V8, there's, you know, liftoff is this baseline tier. And since the Wasm-prechk is, you know, strictly a superset of the information available in normal Wasm, one system you could do is have the sort of baseline tier ignore all of the extra pre-check information and just sort of do what it does today, and then have your optimizing tier, which is, you know, allowed to take a little more time to do its thing to get optimal code. Have just that optimizing tier take advantage of the pre-check stuff, and so then it could spin a little longer on the constraint solver perhaps before giving up.
Yeah, on a similar vein to Thomas's note, the way to think about it is for the optimizing tier, instead of having to leave the de-optimization escape hatch, pre-check would prove that you don't have to worry about it.
Well, it sounds like, so you wouldn't want, so if you said like the browser is required to reject a program because a pre-check failed, then you would have to do it even in the first tier. Maybe, but so I guess there's an issue putting it in the validity of the program entirely. But then again, there's a lot of situations where you're going to have, where you basically are going to know that the local type information isn't enough to eliminate these checks. And so where you, you could have pre-check essentially be instructions hints, I don't know, where you'd say, okay, there is enough information in the local context to guarantee that this thing is eliminatable. Optimizing tier essentially do the checks to make sure that, you know, to confirm because you can't trust this. But that way the optimizing check isn't wasting its time on a bunch of other spots being like that, where it's just not determinable.
Yeah, I think that's a good way to think about it.
Thomas or Luke, it seemed like you had more thoughts.
I agree that hints are a good way to think about it. And, you know, I think in particular, it would be important if this were put into practice, not to let the validity of the module be impacted by whether or not the constraint solver, you know, was able to finish its work, because that would be a portability problem. You know, if different browsers or different engines use different constraint solvers, then they would accept different modules, and that would be hard to predict and hard to control. And of course, if an engine upgraded its or changed its solver, then it could be a backwards compatibility hazard as well, which would not be good. But yeah, treating these as hints would be really powerful. This seems like a sort of a powerful and general way to do hinting for alighting these different dynamic checks in the engine, which is pretty cool.
We potentially could also blend we know this isn't zero with like a bit packing optimizations, sort of the way Rust does, where if you have a non-zero type and you put it in an optional just becomes the all zero for the none type. So it could be used for other, to help with other specs stuff with types that we've been dealing with.
Yeah, I think there's a number of additional optimizations, which is something we're interested in looking at. Also, for example, certain like branch if, we might be able to tell, you know, if you're not going to be taking a branch, for example, and do some dead code, you know, additional dead code elimination.
Have you looked into, I think you hadn't from a chat, but I forget now. if there are sort of smaller constraint languages that are more tractably decidable, like linear or quadratic time decidable, that would be able to eliminate a number of checks?
We've looked at them a little bit. We're interested in taking a kind of a long look at Wasm programs in practice and seeing kind of what the trade-offs are between different constraint solvers and the optimizations that you would get with them.
Mm-hmm. Yeah, that'd be an interesting way to think about it is, yeah, do a corpus analysis and a performance analysis comparison, and then say this linear time algorithm is able to, get this much performance, this quadratic time algorithm is able to get this much performance, and then, bigger performance after that, but you need, cubic or NP algorithms for those. That'd be interesting to, because that, I think, would, I don't know where in that spectrum the team would be willing to affect validity, but like something a linear at least seems like plausible if you were to show that linear time algorithm, type check, or its constraint solving had a noticeable impact on performance and was actually expressive enough to catch a lot of cases. That might be something that could be incorporated as standard, because that shouldn't slow down validity much. But that's what experiments are for.
Yeah, and by the way, I think if anyone knows of any good corpuses for WebAssembly, that would be very useful. And also, I think there are some people here who might have some experience benchmarking some of the WebAssembly compilers, which would also be useful. We've tried to do benchmarking of the compilers, and we've run into a number of issues with just inconsistent results.
Would you say what you mean by benchmarking the compilers? So like you mean benchmarking the output of the performance of the output code?
Yeah, benchmarking the performance of the output code with and without the additional instructions for dynamic checks.
When you've been doing the benchmarking, have you been running the output through Wasm-opt after the fact or not?
I'm not sure.
Are you recommending that he does or does not, Luke?
I'm just thinking that a lot of the tool chains recommend it, like the Rust docs recommend you run through Wasm-opt, because I don't know, for some reason, a lot of the compilers, like Wasm-opt optimizes better or differently on a final Wasm binary, and so they just don't integrate those optimizations into it. And so Wasm-opt will do extra cleanup, but I guess it really depends on the language, whether you think that ecosystem is going to produce Wasm-opt optimized binaries or not, to see if you're better. But I do know it affects code size, which could affect your code cache lines already, which would affect the speed.
Right.
Yeah, in general, I recommend using Wasm-opt for everything all the time, because you're basically just leaving code size on the table if you don't. So in practice, in production, we expect basically all WASMs to be optimized by Wasm-opt today. Wasm-opt is the same as binarian, by the way. It's just the binarian pass runner. So you asked about corpi of WebAssembly. I don't really have a good one, unfortunately, but when I just need some like reasonably sized, more or less real world WASMs, the Inscript and Test suite does have a number of non-trivial programs that it compiles. So I found the Inscript and Test suite to be useful for that in the past.
Nick just posted one too. Oh, sorry, is that?
Sorry?
Nick just posted a benchmark suite from the what's it called, Wasm time that they're building up.
I see.
And I think JP has pulled together like not a benchmark suite, but like a corpus of Wasm, and I think JS embedded Wasm programs from like the web. He's not here today, but I can put you in contact with him.
That would be great. Thank you.
Does anybody else in the audience have any questions, or do you guys have any more kind of prompts that you'd like be interested in getting feedback on?
Well, if people are in, oh, sorry.
I was just going to say one thing regarding benchmarking. Initially, we were looking at the Firefox implementation of WebAssembly, which seemed like a realistic, and I actually had experience building Firefox, so it didn't seem a terrible place to start. But I was wondering if people have a recommendation for some other WebAssembly implementation for benchmarking.
Use Wasm-prechk. It's lovely. It's, may not be in a browser, but we've done some work on it. And I'd be happy to connect you with my grad students who have mucked around in it, but it was pretty easy to work with.
Okay.
Wasm-prechk and Firefox Arch64 use the same code now. So you're kind of testing Firefox, at least, for mobile and new Mac, if you're using just Wasm-prechk. And Wasm-prechk, obviously, you can run faster because you don't have to script the browser with something.
Nick says that he's happy to help with Wasm-prechk as well.
All right, great. So is there, my concern with using something like Wasm-prechk, although you say it's now for at least one of the browsers, is sort of a motivation question. It seems like the browser implementations are going to be the more widely used implementations, or am I wrong about that?
I mean, I would imagine they're going to be more widely used. Benchmarking on Wasm-prechk will still give you some useful numbers, and then you can you can run those experiments on like V8 or something as well later on. But that way you can sort of do formative stuff on maybe like it's easier to run it not on the browser in some ways, just to get some formative analysis, and then you can transport it to the browsers to get to demonstrate more cross-cutting comparisons.
Okay, thanks.
Does actually, do we have any browser team people at the moment? I don't think so, actually.
Ross, am I recalling correctly that the Wasm-prechk implementation was also on Wasm-prechk?
So which one?
The Wasm-prechk presentation, that work was in Wasm-prechk, wasn't it?
Yeah, with Arjun. Yep. So they're also in. I think Wasm-prechk seems to be, at least from the research community, what people are sort of recommending to each other to build on or to modify. So I wasn't sure if that was the case for benchmarking as well, because modifying and benchmarking are different things. And Thomas certainly has probably had lots of experience benchmarking with V8. I'm guessing. I don't know if maybe Thomas has some suggestions.
I don't have a ton of experience with it, actually. I will say that, I would view early performance experiment data from Wasm-prechk. I would regard that just as highly as experiment data in, any of the other web engines. So yeah, I think that's a totally fine place to start.
All right. Any other questions or from either side? Right, sounds good. And thanks a lot, Adam, for the presentation, and thanks everybody else in the audience for helping and all the great questions and discussion. And I'll see you all hopefully next Friday for seeing what Julia compiling WebAssembly is looking like. Bye.
Thanks, everyone.
Thanks.